Today, we're really going to put those things together, put the vector components together, and then add in the vector addition part of it where we actually get a resultant vector. Now, let me give you an example real quickly of one we did yesterday. That's a really simple example, right? We did a really simple one that said, if I moved east and then I moved north, how far did I go, right? And I just had to go find my resultant vector like that, right? We did an example of one of those problems, right? I went east, then I went north, and then I got my resultant. But the issue comes if I've got vectors that aren't perfectly horizontal or perfectly vertical. So what if I left at an angle, and then I went north, and then I went over here, right? Now my triangle looks a little bit different, right? My resultant vector would look something like this. Right, but I don't have an easy way to solve for that purple line, do I? Nope, so that's the trickier part. And so that's what we're going to get to today, is we're going to break down these vectors into x and y, right? We're going to break down those initial vectors into x and y, and we're going to be able to find out what are the sides of that triangle that can help me solve for my resultant vector. Okay, that's kind of the goal here. We're going to find all of the components of my original vectors to help me figure out how far am I from where I started. Okay, so let's going to start with an example here that says, a mail carrier leaves the post office and drives 22 kilometers in a northerly direction. So all that means is that she's going due north, right? She is traveling purely north. She then drives in a direction 60 degrees south of east for 47 kilometers. What's her displacement from the post office? Okay, so here's what I'm going to tell you when we do vector addition. We can draw the diagram, okay? And I'll show you what the diagram looks like. We can draw the diagram, but sometimes I feel like the diagram is more confusing than it needs to be, right? Here's what the diagram would look like, right? She goes north, then she goes 60 degrees south of east, and she ends up down there. And so if I was going to find out how far she is from her starting point, it would look like that, right? But is that an easy triangle for me to solve? Nope, it's not a right triangle. It doesn't do me any good to really draw the diagram. So you're always welcome to, but you don't have to. I'm going to show you how do we work around that, right? How can we solve it without drawing out the diagram, okay? So I'm going to go back to this previous slide here, and we're going to work through that. For vector addition, we've got 3 basic steps we need to follow, okay? Anytime we do vector addition, we have 3 basic steps. And I think it might be worthy for you to write these 3 steps like up higher on your notes sheet, maybe in a more prominent place, because these 3 steps are what we're going to use every time we do vector addition.
Put on our equation sheet?
No, it can't go on your equation sheet, but I just put it in a bigger spot in your notes, okay? Step 1 for vector addition is always going to be to break each vector into its x and its y components. And that's what we worked a lot with yesterday, right? Using sine and using cosine to break those vectors into its components. That's step 1. Step 2 will be to add all of our components together. So that means we're going to add all of our x's together, and we're going to add all of our y's together so that we know what are the components of my resultant vector. Right? That's the goal there. And then the last part of it is to build our final resultant triangle. And so all this will make a little bit more sense as we get through the problem here, but those are our 3 steps, and those are something I think you should highlight. Maybe you should write bigger. You should put them in a more prominent spot in your notes, okay? Because that's going to be really important. Build a new triangle. Okay. So let's go ahead and start with this example based on those 3 rules, okay, those 3 steps. Like I said, I don't think it's really, really important that we draw out the diagram of our motion here. I think we can get to our final problem without having to draw the diagram. I'm going to treat each vector as its own thing. So all I'm going to do is come and draw the first vector, and I'm going to label it V1 because it's vector number 1. And it says it's 22 kilometers north. So I'm going to draw my origin and then draw my vector. So I'm going to give myself a little more room here. Draw my origin, draw my vector. It's 22 kilometers. Okay, and it says in a northerly direction. That means due north. Okay, so I'm going to treat all my vectors individually. So my step 1 is going to be to break each of my vectors into x and y. So my first vector right here, Does it have any x component at all?
No.
No, because it's going purely north. So if I was going to label v1x, it would be 0, right? The x component of this vector is equal to 0. Mm-hmm.
So for every, it's like say v1, we always write vx, or like for each single.
For every vector, we're going to write out x and y. So that's why we're going to label them v1x and v1y. Okay, so what would my y component be then of this vector? It's going to be 22. And is it positive 22 or negative 22? Positive, because it's going north. Very good. Okay, does that make sense? So when it's not at an angle, our breaking it into x and y is really, really simple. Agreed? Okay, so now let's look at vector 2. Vector 2 says it is 60 degrees south of east for 47 kilometers. So it's 47 kilometers at 60 degrees south of east. So I'm going to come over here and draw vector 2. South of east, right? I'm going to draw my vector somewhere in that direction. And south of east, does that mean I need to finish my triangle on the top like that or on the bottom like that?
What do you mean?
On the top, right? South of east. I want to touch the east axis, right? My angle needs to be right there. Okay, so that's where 60 degrees would go. And where does 47 go on that vector? It goes on the hypotenuse, right? Because my vector is going this southeast direction. These, the dotted lines, are the components that make up that angled vector. So we always draw components with a dotted line. Okay, it's helpful to draw components with a dotted line because it helps us remember that's not a vector we were given, it's a vector we solved for, right? The components are the things that we're solving for. So if I was going to label this side, what do you think I would call it? V2x, very good. And I might call this side right here V2y. Okay, do you see why that is? Right? It's the x component of my second vector. It's the y component of my second vector. Okay, so now let's solve for those just like we did yesterday, right? We broke them into their x and y yesterday. So V2x, am I going to use sine or cosine? Right? If x is right here, am I going to use sine or cosine? Tell me first of all, is it opposite or adjacent? The x side, as compared to this angle, is it opposite or is it adjacent? It's adjacent, so I'm going to use cosine to help me do that. Okay, so I'm going to take the hypotenuse times cosine of my angle to get my x component. Okay, hypotenuse times cosine of my angle. And I'm going to go ahead and plug that in right now. 47 cosine 60. And I get 23.5. Or to solve for y, then what would be my next step? Am I going to use sine, cosine, or tangent? Sine. I'm going to use sine. 47 sine of 60. And that gives me 40.7. Now, I think I'm missing something on my 40.7. I think I have to add something there. Do you know what it is? A negative, right? Why do we have to add the negative? Because it's going south, right? It's going downward to get to that. So my x component was moving to the right, so I don't have to add a negative there. But my y component is, okay? So very good. Tell me now, that's all of step 1 right there. Break each vector into x and y, right? We did all of that. Break each vector into x and y, x and y. Okay, step 2 is to add our components. And so what I'm trying to look at now is I'm trying to find what's the components of the resultant vector. It's going to help me find out how far she is from where he started. So I'm going to label these as VRX and VRY. The x component of, I wrote it too. The x component of my resultant vector and the y component of my resultant vector. And I get these values just by adding together my x's and adding together my y's. So my x's are going to be 0 plus 23.5, which is just 23.5. Right? My y component is going to be 22 minus 40.7, which gives me negative 18.7. Okay, I think at this point right here, it's helpful to kind of visualize what direction those components are going to be going. If my x value comes out positive, is my value going to be going east or west? East. So I like to draw a little arrow just to remind myself it's going to be going to the east. And then if my y component comes out negative, is it going to be going up or down? Down. Okay, so I like to draw a little arrow here just to remind myself. So now I've done step 2. I've added my components. My last step is to build my new triangle to help me find out what is the resultant of these two vectors, right? So let's look at our diagram one more time here, okay? If I, actually it's not going to let me while I have it up. Let's just draw it out real quickly. If I went north and then I went southeast like this, my expected resultant vector is going to be going in that direction. We agree? Like that's kind of what our diagram showed us. Now here's my components of this red line. It says we're going to go east, then south. Is that about what we were expecting? Okay, so I just want to check that here. Let's go ahead and finish our problem now. So build a new triangle. We're going to use the components we just solved for to build a new triangle here. Okay, so I'm going to draw my origin. It does not matter if we go south, then east, or if we go east, then south. It makes no difference because it's going to get us to the same final location. You will notice that my pattern when I do these problems is I always work X first, right? That's just my pattern, right? I just do X and I don't do Y because if I were going to do X, Y, and I came over here and did Y, X, I'm inevitably going to get confused when I add them across, right? I just will. So it's easier for me to just always do X first. And that applies to me when I do this here. I'm going to go X, 23.5, and then I'm going to go Y, 18.7. And my resultant vector now is downward to the southeast. Is that kind of what we expected from our original diagram, that our resultant vector was going to look something like that? Right? And so now this is the whole point of my problem, right? This orange line, this resultant vector, gives me her final displacement, right? She's ending up right here in comparison to where she started. So now how can I solve for the orange line? I have to use Pythagorean theorem. Now, it's really important here. We're not plugging in the negative when we do the math part of it. The negative just tells us that we needed to go downward. We don't plug in the negative when we do Pythagorean theorem or when we find the angle, right? The negative just tells us direction here. All right, so I'm going to go Pythagorean theorem with those two.
We square the final one.
Yep, in my calculator, I do it in one step. I go second square root of 23.5 squared plus 18.7 squared. Right, you can do it in one step, so you don't have to keep plugging things back in. It would be measured in kilometers, so that's only part of my answer, though. 30.03 kilometers. So that's telling me that if she leaves the origin, she needs to go 30.03 kilometers. But is that enough of an answer for me to tell where she is from where she started? No, I have to have direction. So can I just say 30.03 kilometers southeast? Nope, I have to find the angle that goes with it. I have to, because otherwise she could leave any direction, go 30.03 kilometers, and she's not going to get back to where she wanted, right? She's got to leave at a specific angle. So I'm going to find that angle right there, right? This is where we use second tangent, right? The inverse of tangent. So to find my angle, I'm going to go tangent of opposite over adjacent, right? That's going to give me this angle right here, right? Opposite over adjacent. So second tangent of opposite over adjacent. And that gave me an angle. So we're going to write it at an angle of 38.5 degrees. And then what is it? Is it west of north? Is it south of east? Is it east of north? You have any idea? South of east. Very good. South of east. Okay. How do we feel about that? Okay. It's a lot of work, but it's just basic algebra, right? The scope of work is a lot, but the actual difficulty of the work is not, right? The biggest part with vector addition problems is that you have got to stay organized. Your paper has to have very clean writing, very clean diagrams, very clean organizational systems, right? So you've got to get yourself into a system that works for you, but we've got to make sure that we're really paying attention to detail. When we do this part of our problems, we have to include the negatives if we have something moving south or west. We have to put the negative on that component. All right. This one says, add the following vectors. Actually, let's skip this one. Let's go to the next one first, and then we'll come back to this one, because that one's a level of degree, or one level of difficulty up. So let's go to this one first, then we'll go back to that last one, okay? So this says, Jim walks 5 kilometers due east. He then turns and walks 6 kilometers due south. Finally, he walks 7 kilometers at 70 degrees north of west. So there's 3 different vectors here we have to take into account. So does drawing the diagram of him walking, does it do us any good here? Because it's not going to make us a perfect triangle, is it? Right? If he was just going east, then south, then stopping, then we could do a perfect triangle, but he doesn't. Now he goes like this. Right? And so it doesn't give us a nice pretty triangle to solve. So drawing the diagram doesn't really do us any good, right? So we're just going to treat each of our vectors individually. Okay, we're going to start with this orange one here, 5 kilometers due east. I'm going to call that vector 1. All right, and I'm going to draw out just that vector. Right, it goes purely east. So tell me what our first step is with our vectors. Finding x and y. Break each vector into x and y. So what would v1x be equal to here? 5, right? And is it positive 5 or negative 5?
Positive.
It's positive. So v1, x is equal to 5. What would v1y be equal to? 0. Very good. Okay, very good. My second one is the red one here. V2 says he walks 6 kilometers south. So that means v2x would be equal to what? 0. 0, because I have no x component in that vector at all. v2y would be equal to negative 6, right? Because it's going south. All right, then vector 3 says it's 70 kilometers at 70 degrees north of west. So I'm going to draw my origin. I know my vector is going to go somewhere north and west. Then I've got to figure out how do I complete my triangle there. 70 degrees north of west. That means it needs to touch the west axis. So I'm going to complete my triangle that direction. Does that kind of make sense how that gets done? Right? Whatever direction comes last, that's the axis it has to touch. So that means this angle right here is 70 degrees. And my hypotenuse is what? Seven kilometers, right? That distance or displacement has to be my hypotenuse. I'm going to use cosine, right? Here's my x side. That's what I'm solving for. I'm going to take the hypotenuse times cosine of 70. So that gives me 2.4, 2.39. And so what else am I missing there? Has to be negative, right? Because my object is going to the west. Okay, so negative 2.39. And then if I'm solving for v3y, the y side we said is the opposite, which means we're going to use sine. So 7 times sine of 70 gives me 6.58. And should that value be positive or negative? Is this component going up or down?
Oh, I'm sorry.
Right, to get to our final spot, it had to go up.
Okay, I see.
Right, we're working on getting to our final location. So I had to go west and I had to go north. Go back and look at your original thing, north and west, right? So there's our parts of our components as well. All right, now we've done step 1. What is step 2? Add our components. So we're going to add all of our x's, add all of our y's. I'm going to make this a little bit smaller so I can have room to do that. Okay, so we're going to we like to call the final ones what? VR for resultant x and VR y. So my x's are going to be 5 plus 0 plus negative 2.39. 5 plus 0 plus negative 2.39 gives me a value of, I got 2.61. Let me know if you agree. Okay, and so if that number comes out positive, does that mean it's going to be moving east or west? East. So I'm going to draw a little arrow there just to remind myself. Okay, so I've finished my x components and my y components just by adding my components across. Now I'm going to build a new triangle. Like I said, I like to start with the x. It makes no difference the order in which you add them, but I'm going to go 2.61. And then I'm going to go 0.58. Right? And I want to try to draw that kind of to scale, right? Not that we're having to get out a ruler or anything, but we want to think about if this vector is, 2.5, then this needs to be approximately 1/5 of that length, right? Just being able to think through that scale, okay? And so now this means my final resultant is my red line right there. And so I need to find the hypotenuse and that angle that goes with it. Why don't you guys go ahead and try that, and I'll give you a jump start on that.
Which place should we write out to? Just 100?
Okay, that's what I got for this triangle that I drew right here. Let's say that once I got to this, I had drawn my angles in the opposite direction. I had went north, then I went east. That's fine. It's still getting me to the same final location. My hypotenuse is still the same. It would have been 2.67 kilometers at this one would have been 77.5 degrees east of north, right? This angle and this angle are complementary of one another. They add up to 90, right? This one is 12.53 degrees north of east. This one is 77.5 east of north. Those are both acceptable answers, right? You will not have to give me both answers, but they are both acceptable. They both get us to the same final location. So you don't ever have to have both, but your angle could be valid even if it's different from somebody sitting next to you, right? As long as they are complementary and as long as you've got them labeled correctly, right? 77.5 degrees north of east would not have been acceptable because that would have got us, that would have put us at a different final location. Okay? All right, so you're going to try this one on your own. So this one doesn't even give you a word problem. It just says add the following vectors. You've got 3 vectors here you've got to take care of. Notice that 2 of them are at angles, right? So you're still going to treat each of them individually. There's no reason for you to draw them out. Just treat them individually. Break them into your x's and y's. Add your x's and y's, build your new triangle. Okay, I'm going to give you a little head start on this one. right, do you guys already have your triangle done? Or not quite yet? Yeah, do you have your resultant done and stuff like that? Okay, that's fine. Go ahead. You might be a little bit ahead of me, so I'm gonna keep working and see what we get. At second tangent 88 degrees north of west.